be in here. Let's see, make sure it's somewhere around there, and it should be somewhere around here. Okay. All right. Now that you've ruminated, normal force. Where? What?
Upward on the void
Okay.
and downward on the void.
Yes, that's the force that he exerts on the board. So I have this normal force going up, normal force going down. Now, if you've read the book, you might look at that and go, well, this problem is it's a lot simpler than we're making it. Right, I'm just trying to connect some of the stuff that we've done before. We are taking the long route, the long path to get this. We are assuming it's all in equilibrium. Which means what?
So
The net force,
zero and
equal-
change in velocity is zero.
And
net force equals 0.
yes, and that's the one that applies directly to what we're dealing with right now. We've got those three conditions. So the net force equals 0. So if he's in equilibrium, and he has two forces acting on him. We have this normal force holding him up and this weight trying to pull him down. They have to balance out. In other words, if I drew it, when you add vectors, you add them head to tail. We have normal force acting up. And now I'm here. And then weight acting down. And we should end up back where we started. If it's an equilibrium, when I add the forces, we end up back where we started. Because the resultant is from where we start to where we end. And so, in essence, what I'm saying is that the magnitude of the normal force must equal the magnitude of the weight. Thus, when you're standing on a scale, the scale is really measuring normal force, but if you are in equilibrium, the value should be equal to your weight. But how do we find the weight of the person? I know his mass, but how do you find weight? Well, we're in luck. Unless you're using an audio reader, then you're not in luck. There is it's known as Newton's second law. The fact that force and acceleration are proportional, with mass being the constant of proportionality. This is what I consider the most important formula in all of physics. It is something that we will visit again and again. So this is the total force is equal to the mass times the acceleration of an object. Now, this is a chapter 4 thing, but it does come in handy when we're talking about how to find the weight of an object. So if I have an object in free fall, for those who need the visual, while it is falling, what are all the forces acting on it? Bless you. We did this one already. Force diagram of object in free fall.
Just wait.
You stop in there?
Would you have weight acting up?
On the ground. Okay. Any other forces acting on the ball?
Gravity. Gravity.
That would be weight. Okay. So in the case of something falling, the net total force is its weight. And the acceleration of an object in free fall is known as the acceleration due to gravity. This little g right here equals acceleration due to gravity. It is not a constant, but we often treat it as such. Not constant, but close enough if change in the height is small. And what I mean by small is, if you think about the size of the Earth, small compared to the size of the Earth. The value of G at the top of the Empire State Building is close enough to the value of G at the bottom of the Empire State Building. So we consider for things that are, within a couple miles of the Earth's surface, it's constant, close enough. Anyone happen to know what the average value is near the surface of the Earth?
Was it 9.8?
Do you know units?
I can't remember that. I just remember in the book what the number was.
All right, 9.8 is the number if you're dealing with metric. 9.8 meters per second squared. Instead of an equal sign there, I should put the squiggly one. It's approximately equal to G. So if you see 9.8 meters per second squared, they're probably talking about acceleration due to gravity on Earth. Hewitt oftentimes just rounds it off to 10, just to make the math easier. Now I want to emphasize the fact that it is not constant. G, for Winston-Salem, 9.798 meters per second squared. There have been two major studies to try to find the acceleration due to gravity throughout actually the world. The first one actually might have just been the US. The more recent one was done they flew a plane with a sensitive equipment all over the US. They basically had a grid pattern, and so they found acceleration due to gravity that way. And then in the 70s, I believe it was, they planted various instruments throughout the country. And the one in Winston-Salem, one of the ones in Winston-Salem, is there's this road right out here that tees into Silas Creek. In the median, right where that road sort of hits, they had the spike right there, which is about this level, 9.798. If you are in, I think Rome is 9.800, and so it varies depending upon where you are in the world. So in the labs, if you see 9.798, or if I haven't corrected it, 9.796, I made a mistake the first time I did it, so a lot of labs, I'm slowly changing those. But if you see this is because this is true for Winston-Salem. So, over here, we assume this is some generic place on Earth. And so the weight of the person is going to be the mass, 100 kilograms, times generic value Now, my comment that you're not necessarily in luck if you're using an audio reader is because all of the readers that I have heard, when they get to mg, they read that as milligrams and not mass times acceleration due to gravity, which is a real detriment to any physics textbook, because every physics textbook is going to have mg in there somewhere, not meaning milligrams. I was looking at audiobooks at one point and had access to it, and basically told one representative that was a deal breaker. There's no way I would endorse any book that misread that. All right, so do the math. So it'll be 980. And then units. Well, I have units of kilograms and units of meters per second squared, and I'm multiplying. So it would make sense that is a kilogram times meter per second squared. We treat units, when you multiply units, it's just like anything you're multiplying, it's just 1 times the next thing. And the kilogram meter per second squared is too much for physicists to write. That is a Newton. So by definition, and we'll put it up in, I guess this corner is a little bit more centrally located, 1 Newton. I have 3 lines there. When you see the equal sign with 3 lines, that means it is true by definition. There's no derivation, there's no interpretation. It is the powers that be sat down, they said, we are going to say 1 Newton is a kilogram meter per second squared. So we now have his weight, which is 980 newtons, and therefore the normal force is 980 newtons, which means this normal force here is 980 newtons. What is the weight of the board?
50 kilograms?
Ooh,
Oh.
I'm definitely going to say no to that, very vehemently, no. Now, some students I've done that to suddenly shrivel and never speak much anymore, but I do want to emphasize, this is a mass.
Right.
Despite what the biology instructors tell you, and the life sciences people, where I've heard them say a weight in kilograms, and I cringe. In physics, we cannot make the assumptions that the biology people do. We are not limited to life on Earth. The universe is our playground. How would you find the weight of the board?
The same way you found the weight of a person.
Which is?
You want total 900, that's 980 newtons.
That was for the person. What is it for the board?
Well, it would be half of what the person was.
Okay.
50, so 490.
Yes. Plug it into the exact same formula. The weight of the board would be 50 times 9.8, which is 490. All right, questions to hear before I erase? Probably the stuff on this side.
I was just wondering about the tension on the ropes. Why you only draw it one way and you don't have to draw it like from the,
Draw the other one.
yeah.
Generally, when you get into the meat of a problem, you realize there's some things that really are not particularly of importance. So if we actually did, I'm going to quickly go through if we did the full thing. So I have some sort of board here. This is attached to a ceiling up above it. I have a person standing on the board. This is attached to, let's say it's part of a building, and then I have ground down here. So I think this is self-contained at this point. If I did the force diagram, I have the board, I have the rope, I have the person, I have whatever this top structure is, I have 2 walls, and I have the ground. Actually, we could treat that as a building, and then I have the ground. So what I really care about is just the board, that's the main thing. But we have a tension acting up here, we have a tension acting down here, we have a tension acting up here, we have a tension acting down here, we have some tension acting here, tension acting here, tension acting here, tension acting here. We have a weight of the building, weight of, I'll just ask for structure, weight of structure, weight of board, weight of board, weight of person, normal force up, normal force down, and, normal force up on structure, normal force down on ground. All right. So if we did the whole self-contained thing, it would look something like that. I might have left something off, but that's hopefully the gist of it.
Okay, thank you.
And ultimately, all I still care about is just that. And part of it, as you get to more complex problems, part of the experience aspect of it is you learn to go, oh, I know I can ignore that. So, sorry to change you, I was just hoping to
Okay, thank you.
cut out some of the extra. Any other questions at the moment? All right, so let's clean up our forces acting on the board there. Let's see if we have a dark enough color. So I have that 600 up on the left. I have 490 acting down in the middle. I have this 980 newtons coming from the person, and then I have some tension acting up here. Because ultimately I have the four forces acting on the board. The board is in equilibrium, so the total force better be 0. Which means the total forces up must equal the total forces down. From an addition point of view, sorry, voice changing. I go down 980 newtons, because again, it doesn't matter which one I start with. I then go down another 490 newtons. Then I'm going up 600 newtons. And since I'm going to end up where I started, because again, the total force is 0, so I better end up where I started. That's the tension we're trying to find. That's our unknown. Ultimately, if it's in equilibrium, the forces in one direction must equal all the forces in the other direction, magnitude-wise. Obviously, direction will not be the same. So doing the fancy math here, 1470, going down. Therefore, 1470 must be holding it up. 600 have already been accounted for. So this has to be 870 newtons. So I've done my math right. 600 plus 870 is equal to 1470. Questions? We were about to wrap up chapter 2. We're getting close to it. I'll leave that up there. Oh, having trouble
No,
reading?
I'm talking to myself, sorry.
Okay. It looked like you're trying to see that stuff and not the stuff I just erased. I should have
I am.
asked.
I got myself there.
If you miss the stuff on this side, it's still here. Actually, it should be recorded. centuries from now, people will be able to look back on this moment. I wonder how many backups YouTube has. Are they just one small glitch away from everything being lost? I know I've asked this already today, but we'll do it again. What are the three things that tell me that something's in equilibrium? And wait, before, and without looking at your notes, how many can you get? Three meanings of equilibrium. I wasn't expecting people to be stumped on all three of them.
No change in velocity.
All right. There's one. Okay, look at your notes if you have to.
Natural force equals what?
Two issues with that. One, that's not a general condition for equilibrium. That just happened to be true for that one case, and it's normal, not natural.
I'm sorry.
At this point, when people say natural force, I know what they mean. However,
Acceleration is 0.
yep, there's another one. And the third one.
Friction is equal to 0?
Not friction.
Or
Yeah. Force. Total force. Net force. That's sort of right there. All right. Again, if one of these is true, the other two are true. So if I have an object that is moving along, let's just make it middle of space. There's nothing there except for this one object, so I'm not worrying about any other forces. It's cruising along at 50 meters a second. At what point will it stop? The only way that you can have a change in velocity is if the net force is not 0. Things will keep doing whatever they're doing until some net force acts on them, non-zero net force acts on them. This property to want to continue doing whatever you're doing is known as inertia. Inertia is a concept, first off. So tendency of an object to maintain constant velocity several ways to word it, until an outside, like I said, just put some clarifiers, a net non-zero force acts on it. And really what he is saying is that objects want, as a natural tendency, they want to do whatever they're doing. Which brings me to my biggest issue with Hewitt. Ugh. every time. When they went to the new edition, to the 12th edition, I thought, oh, maybe they changed it. Over here in a bubble on page 26, Hewitt uses the unfortunate terminology. You can think of inertia as another word for laziness, parenthetically, or resistance to change. I'll agree with the resistance to change, but that's not laziness. If I'm out digging a hole, if I'm lazy, I want to stop digging as fast as possible. Resistance to change is once I start digging the hole, I want to keep digging it. I don't want to stop once I start. Now, I don't want to start to begin with if I'm not doing it, but once I start it, that's what I'm going to keep doing. And for the next bit, I did get my daughter's permission to use this. Except when I had her in class, she did not want me to use it during that time, but other than that, she was okay with it. But growing up, my wife and I called our daughter Inertia Girl. Because she'd be at home, we have to go to the store, she'd be too young, we couldn't leave her. Despite Romulus and Remus's success being raised by wolves, we did not want to leave our daughter being raised by the dogs. So we need to go to the store, we want to take her with us. She didn't want to go. So we get her into the car, we get to the store, she doesn't want to get out of the car. We get her into the store, it's time to leave, she doesn't want to leave the store. We get her into the car, get home, we go inside, she's staying in the car. Whatever she was doing, she wanted to keep doing. Now, how much of it was because she was a redhead, I don't know, but that's the little girl that I still picture in my mind, even though she's married and she just made a successful bid on a house. But I still picture her this big. Sorry, it's going to get a little teary there. All right, physics. So inertia has the tendency to want to keep doing whatever you're doing. Newton summed this up in Latin, so I won't do the Latin part. In a much wordier version, I'm assuming that most of you have heard this before. An object in motion, and I'll try spelling correctly. An object in motion stays in motion. Now, parenthetically add at a constant speed and direction. Unless acted upon by a net non-zero force. And the other part of that is, for some reason it generally gets split out. An object at rest stays at rest unless acted upon by a net non-zero force. This is a huge departure from the ancient Greek philosophy.
Which law is this of Newton? Which law is this of Newton?
This is Newton's first law. Newton's first law of motion. He also has laws of planetary motion. This is Newton's first law of motion, which is abbreviated, I will abbreviate it as N1, it's supposed to be a 1 there, N1L, Newton's first law. Now, I'm not quite sure why he bothered writing Newton's first law, because Newton's second law covers this. Just Newton's second law is the math version of this. So if I take an object, and we'll just take this box right here, and I push on it on the table. Question is, why does it stop? The ancient Greek belief, the belief that was in place for 2,000 years, was that it stopped because it wanted to be at rest. Newton comes along, and he is standing on the shoulder of giants, but Newton comes along and summarizes it all. Basically says it stops because something forces it to stop. If that friction were not there, it would just keep going until some other force acted on it. But the natural tendency is to want to keep doing whatever it was already doing. Because of the connection here, Newton's first law sometimes is just referred to as the law of inertia. So, since inertia is a concept, how do you know which objects have more inertia than others? I think I'm safe on this one. Do I have more inertia than any of you, or do you have more inertia than I have? Or is it the same? Kind of like there was a question mark in that answer.
Would it be higher if you're actually in motion?
No, the tendency is going to be the same. The amount of, let me circle back to that one. There's some other things I want to bring in first. All right. So think about it this way. You put an elephant on roller skates in the hallway. And then you put just an ordinary dog on roller skates. And I'm doing roller skates just to minimize the friction. You push on both of them. Which do you think is going to change what it's doing more?
No,
Why?
this small,
All right.
that's way minor.
Almost there.
Mass,
Somebody just said it?
mass.
Yes, less mass. Now, the mass and the weight are related to each other, and the mass is related to the size because their densities are roughly the same. However, specifically, it is the mass. So the quantification of inertia, the thing which tells us what has more inertia, is the mass. So mass is quantification, because I can't think of a better word right now. It's the number which tells you which has more inertia. A couple years ago, there was this big to-do in physics about the Higgs boson. The Higgs boson is supposed to be an explanation for why this is true. That's well beyond the scope of the course, but just in case you've heard of Higgs. It was the theorists trying to come up with explanations for, well, any theorist thing is you come up with rules and then someone goes, well, why is that true? And so they dig down deeper and there's anything that's not unallowed, they're going to make it up. All right, questions to hear? All right, I think at this point I'm officially going to say I'm done with chapter 2. So, because of that, let's talk about quiz dates. So if you'll notice, in chapter 2, if you don't have the book, then you'll look at it later. There's a think and solve, think and rank, think and explain, and think and discuss. Some chapters will have a 5th section called plug and chug. Now, if on Blackboard, if you go to assignments under chapter 2, there's 2 documents there for chapter 2. The first document is just problems from the textbook listed. These are the ones that I suggest you look at. The second document is the same thing except it has the solutions. So I'm not going to collect the homework. This is for you to help you study. What I'm going to do of the assigned problems, I'm going to take one of the think and solves that I've assigned to you, one of the think and ranks, one of the think and explains, and one of the think and discuss, and that will be the quiz. Potentially, you have no idea which ones I'm gonna pick. Although some students start playing the game at some point of trying to guess which ones I'm gonna pick. Sure, why not? So, because you have the questions already, you have, this many questions, and, I'm picking this many, and you have solutions, in theory, you should know all the answers before you walk in. If you try to memorize your way, from what I have seen in the past, if you are huge into memorizing, that will work in the short term, but at some point, that is not a good strategy. Please don't try to memorize. I had once, this was with a 251 course. The student had memorized exactly the book solution. Now I changed the numbers, because anything with numbers in it, I feel free to change. You should still be able to do it. The person wrote down the exact solution, and this wasn't a simple one, wrote down the exact solution to the given the numbers in the book, not the problem numbers on the quiz itself. So that's probably the most extreme case of they had it memorized so well that they had no idea what the question was asking.
So all of those, are ones we should do, because they're some of them are gonna be on the quiz.
Yes,
Okay.
yes. There is no question on the quiz where I cannot point to, hey, here's the problem it comes from, and you can see right here, it was assigned. If you like surprises, you can come in completely unprepared. Also, not a general recommendation. And I like to, in general, have one class in between when I'm officially done with the chapter and when the quiz is. And so that puts us Wednesday, the, yep. Is that October? There's September. 9 to quiz. Homework quiz on chapter 2. Oh, I guess I should put it.
No, it's just chapter 2.
So next Monday would come in, I'll start out with any questions. And then if you have questions about the problems, that would be a good time to ask. The day of the quiz, I'll often start out with any questions. The difference is on Monday, since we're not having the quiz on Monday, but Wednesday. On Monday, I'll take however much time I need in order to answer your questions. Wednesday, I might cut it off at some point and say, listen, we gotta get the quiz done. So also, if you notice the two documents there, there's also some links just below it in Blackboard for chapter 2, and that's where I talk through every single one of these. Most of the time, I believe students don't really look at those, but last fall, I had a set of students who basically thrived on those. And so I think at this point I have that thing for every chapter where we have questions, where there are homework assignments, at least up until we get to electricity. So that's another resource available to you. All right. Any questions before we start talking about motion? I would like someone in as much detail as possible describe to me how to get to the bathroom from here. Does anyone know where the bathrooms are? Oh, they're on the other side of this wall. If you come up the steps and instead of taking a right to come to here, if you took a left, about halfway down the hallway. That's where the bathrooms are. Ladies' room, men's room. Or tell me how to give me explicit instructions about how to get to the stairs.
You walk over, open the door, walk
Wa-
out.
Walk over, open the door. How do I get there?
Take the straightest path from where you're standing and walk. And then open the
The
door.
straightest path.
The straightest path to the door from where you're standing,
So you want me to go to my right?
yes.
Okay.
And then open the door,
How far do I go to my right?
however many feet it is.
Just give me a number.
Like 20,
All right, so 20 feet to my right.
yeah.
Open the door.
Open the door, then turn to the right. Walk another 25, 30 feet.
I will contend that's impossible. All right, so walking, let's just say, assume it's 20 feet. I open the door and then turn right and walk 20 feet. That's what I got. Did I miss something?
Walk out the door.
How far?
3 feet.
All right, 3 feet, 5 feet, we'll split it, 4 feet. So I walk out 4 feet and then what?
Turn right.
Okay, and then
Walk straight until you get to the door and turn.
how
left.
far?
Like 5 feet.
All right, so 25 feet. So then I turn right, take 25 feet.
Turn left.
Okay,
Open next week. Open
all right, so as you're giving me instructions, as I was trying to get you to do and give me detail, there are two things involved. How far and in what direction? Hey, vectors. Matter of fact, in some classes, I make it even more excruciating. I'm starting to hear, what do I need to do to get there? Well, because if I turn this way, there is one thing I have to do in order to get to the door. Sorry, I'm not hearing the.
Walk.
Yeah, but in terms of describing the motion, I have to speed up because I'm at rest right now. Now, when we are trying to describe motion in physics, there are certain things certain key terms. There are 4 major ones that we will deal with in more detail than you dreamed even possible. Position, displacement, velocity, and acceleration. These are key terms when talking about motion. Matter of fact, these are all vector terms. If I ask what is the displacement, that is a vector I am asking about, so magnitude and direction are both required. Velocity is a vector quantity. If I ask what is an object's velocity, I'm asking for how fast is it going and in what direction. There are scalar analogs for these. For most of them at least. Displacement, the scalar analog is distance. So if I'm asking what is the distance traveled, I'm not asking a vector question, I'm asking a scalar question. The scalar analog of velocity is speed. And then fortunately, the scalar analog of acceleration is acceleration. But at least with speed and distance, automatically, just based upon the word I use, you should immediately think scalar. The other two, displacement, velocity, position, these are all automatically vector. And then we'll talk about how I differentiate between the accelerations, say on a quiz or test when I ask what's the acceleration, how do you know which one I'm asking about? Of course, physicists don't like writing these words down, so we use symbols. Position has several symbols. I use X a great deal. Some textbooks will use X, Y, or Z to represent, horizontal, vertical, and depth. I tend to use X for whatever. S is used as a generic term, and the other most common one used is R. R comes from radial, so generally if you have some central point and you're talking about moving away or towards a central point, that's when you tend to use R. S comes from the Latin, stadia, which was basically the ancient Roman mile, or their equivalent of that kind of distance. And then X, Y, and Z come from the brainwashing from the math reader. Position is where an object is with respect to, that's WRT, with respect to the origin. And in parentheses, I'll put down 0. If I have a number line, and a number line has a 0 on it, we generally don't call that the origin, we call it 0. But once you get axes, you have the origin, that's where they meet. So if I have, let's say, a coordinate system like this, and I have an object sitting right here, that would be the position, and also X sub I. The little subscript I here means the initial position. So I have an object that's sitting right there at some initial position. Questions to here? There is no scalar analog of that. I played around with location at one point, but that didn't feel right. Displacement is can be defined one of two ways. It's either the change in position, or it is where an object is with respect to the starting point. Because it is change in position, we use the shorthand notation for change. And what is the shorthand notation for change? Otherwise known as delta, capital delta. So displacement is delta x or delta y, or delta in front of whatever you're using for position. So if I start in this location and then I end up here, that is my final position. My displacement is from where I started to where it ended. That is my displacement right there. Displacement in purple based upon my initial position and final position. Velocity change in position over change in time. Or how fast an object moves. And in what direction. And the symbol, as I've used in class already, is v with a vector symbol over it. And acceleration change in velocity over change in time, or sometimes referred to as the time rate of change of velocity. In other words, at what rate is velocity changing? And the symbol, at least the symbol's easy, and with a vector symbol over it. Questions to hear? All right. Let's talk about the scalars for a moment. Distance is just how far an object has moved. It's not relative to anything, it's just how far an object's moved. The symbol, though, is basically, the symbols for these three are basically this without the vector symbols. So, delta x, delta y, just no vector symbol over it. Speed is just v, it is not s, it's v. And acceleration is just a. Speed is change in distance over change in time, or distance over time, sorry. It's distance over time. Acceleration, scalar acceleration is change in speed over change in time. So let's illustrate some of the differences between them. They start in Columbia, South Carolina. In Winston-Salem, we'll just simplify it, it's 200 miles north. Close enough for what I want to do. So 30 years ago, I lived in Columbia, South Carolina, and now I'm in Winston-Salem. If I consider this my starting point, what is my displacement over the past 30 years? Keep going.
North.
Yes, direction matters. So my displacement for my last 30 years of life, my displacement is 200 miles north. Doesn't seem like particularly much. However, the distance I have traveled, I did consulting for a number of years. I was driving at least 1,000 miles a week. But let's say we're driving it and you check your car's odometer at this point, and then you start driving, you decide to take the leisurely route and you're going around visiting small towns. And the change in the odometer on the car is 500 miles. What is the distance traveled? Was not expecting the silence on that one. No, not two. You said 200?
200.
No. There's only one other number up there. Yeah, 500 is the distance traveled.
Oh, distance.
Oh, sorry,
Okay, so.
distance. So recognize that when we're talking about displacement, it really cares about where do I end up relative to where I started. It doesn't matter how I got there. It doesn't care about the in-between. It just cares about where am I relative to the starting point. Distance cares about all the little things in between. And this brings up a particular awkward notation. Often, if I'm talking about force, force is a vector. I put the little symbol over it so you all know, we're talking about a vector force. If I want to talk about the magnitude of force, so if all I care about is just the magnitude, I can symbolize that, if you flash back into your notes, as an absolute value sign around it. But oftentimes, we can just write F without just drop the vector symbol when I'm talking about the magnitude. But recognize that doesn't necessarily work here, because if I just drop the vector symbol to indicate the magnitude of the displacement, I'm not getting the distance. The magnitude of the displacement is 200 miles. The distance is still 500 miles. So when I'm talking about magnitude, usually in a quiz or test, I will say, what is the magnitude or the size? And I will try to use the absolute values symbol notation of it instead of just the letter without the vector symbol over it. There are many cases where you can get away with this, but there are other cases where you cannot get away with just dropping the vector symbol to represent the magnitude. Velocity versus speed. I'm now going to race Usain Bolt around the track. I'm assuming Usain Bolt is still the fastest man alive. Or ever, actually. So Usain Bolt and me. I'm going to contend that I am faster than Usain Bolt. But only if you look at it the right way. So we start out, gun fires, Usain Bolt goes all the way around the track in 40 seconds. I go all the way around the track in 200 seconds. Well, let's figure out our average velocities. Velocity is change in position over change in time. Technically, that is the average velocity. The average velocity is the change in position over the change in time. So when Usain Bolt starts out at the starting point, goes all the way around, ends up back at the starting point, what is his displacement? In 40 seconds. So it's 0 meters in 40 seconds. So Usain Bolt's average velocity is 0 meters per second. I go all the way around the track, end up back where I started. What is my displacement?
0.
So my average velocity is 0 meters over 200 seconds. So it looks like I'm just as fast as he is. Now, instead of looking at it that way, when he finishes, I'm probably somewhere around here. Who has a greater displacement? Because his is 0. Mine's not 0. Which means my average velocity at that point is greater than his. I am faster than Usain Bolt. The first one, we both got nowhere. He just did it in less time. But I prefer to think of it the other way. Now, I'm not talking about speed, and I'm not talking about instantaneous velocity. So let us bring in some extra vocab here. When talking about velocity, there's actually instantaneous, and then there's average. If I just say, what is the velocity? Instantaneous is default. If I want average velocity, I need to specify. Same with acceleration. There's instantaneous, and then there's average. If I just say, what is the acceleration? That is the instantaneous by default, if I want the average acceleration, I need to specify average acceleration. Now, a lot of the times we'll deal with constant acceleration, so instantaneous and average will be the same, but not necessarily every time. And then displacement, there's instantaneous, and then there's overall. Unlike the other two, if I ask what is the displacement, overall is the default. So right here, when it got to the end point, I asked what is the displacement, I was asking the overall displacement. I'm not talking about the displacement from a moment earlier. So what really is the starting point? If you were doing your own displacement, would you do it based upon where you woke up this morning or where you were born? Assuming you didn't wake up where you were born. Now, acceleration, got the same word, and I've gotten much better about this. Occasionally I do forget. If I want the vector acceleration, then after the acceleration, I'll put that symbol with symbol. If I want the scalar acceleration, then I'll put just the letter A after it. So I will specify, I want what is the acceleration, comma, and then either that A or that A with a vector symbol. So you know which one it is. If you're looking at, if you're on a test or quiz and I use acceleration but forget to do that, just ask. But as a general rule, the vector one is, usually it's the vector one that's being asked. Questions up to here? Now we talked about before, if something's traveling in a straight line, I think we've talked about this before. It's something, if you're dealing with one-dimensional motion, you can get away with indicating direction with just a plus minus or zero. If you're two dimensions, you have to use I hat, J hat, but here in one-dimensional motion, you can get away with plus minus or zero. So the sign, plus, minus, or zero. Position is positive if on plus positive side of zero, or origin. So I'm now about to walk back and forth in front of the board, and so I'm just going to arbitrarily make that my origin. Right there. And I'm going to make to the right positive. Therefore, right now, is my position positive, negative, or zero?
Positive.
Yes. Why?
Because you're on that side of zero.
Right. There's zero over there, I'm on the plus side. Now, as I'm doing this, we're going to go through several of these. I don't want to get into parallax issue because Matthew and Joanna probably have the most extreme views. If I'm standing here about at the origin, I'm supposed to be at zero, even though it looks to you like I might be on the plus side, and it looks to you like I might be on the minus side. But if I'm around zero, I'm at zero. So, what's my position now? Wow, so quiet. We could do that in unison, I bet. What's my position now? Some of the voices were so in sync, it did not sound like more than one voice. What's my position now? We're going to be doing more of these. Chime in. Since I can't see your mouths moving, I can't necessarily identify who's actually saying wrong answers, so go for it. Displacement, overall displacement, is positive if on positive side of starting point. So for the sake of this exercise, I'm gonna make that my starting point. Now, positive direction is to the right, that I identified it once, I don't have to identify it again. So, give people a chance to write down, maybe that's what threw people last time. Get rid of some of the clutter. All right, so here we go. Get ready. My position, positive, negative, or zero? My position, positive. Position cares about that. My displacement. There we go. My position. My displacement. My position. Everyone can play. It's not just a few people. My displacement. All right. My position. Displacement. Same game. New thing. Velocity cares about the direction you're going in, so it is positive if moving in positive direction. Obviously, negative is moving in a negative direction. Okay. Sometimes this is going to require a quicker response. I might rewind if people don't respond quickly. All right, here we go. My position.
Positive.
My displacement.
Negative.
My velocity.
Negative.
My velocity.
Oh, positive. Oh.
Negative.
Please.
Positive if you're moving in a positive direction.
Right.
Yeah.
The question was asked when I was still doing this.
Oh.
Right, negative.
Yep. Oh,
No, positive.
positive is that way.
Oh,
Yeah.
Or are you changing the coordinate system?
no.
Just being a rebel. All right, velocity,
Negative.
position,
Negative.
displacement,
Negative.
velocity,
Positive.
position,
Negative.
displacement.
Negative.
Okay. Velocity,
Zero.
and now the tough one. There are two ways of looking at acceleration. At least we've talked about forces already, so it's a little bit easier. Most textbooks do this stuff first, and it's nice if acceleration, it's nice if you've done forces before you do acceleration. It's also nice if you've done acceleration before you do forces, but what can you do? All right, so acceleration is positive if net force is in positive direction. Negative if net force is in negative direction, and zero if net force is zero. That would be equilibrium. Or if speeding up, velocity and acceleration have the same sign. If slowing down, velocity and acceleration have opposite signs. All right, give people a chance. So right now, my velocity is, okay. If I stop, so I'm going to go in that direction again. I'll have negative velocity. If I stop, what is the direction of the force that has to be applied to me to get me to stop? That's all. Not sure, Taylor? Or Shay? Turn it. Why him? Shay. Sorry. Jay, it looked like you started to point and then you stopped.
Yeah, the force is gonna outward use.
Okay. So the force, if the force, I saw two people point in that direction. There might have been more. If the force is in that direction, what was my acceleration as I stopped? Yes. Another way of looking at it, I was moving in this direction and I stopped. In order to stop, I have to slow down. Since I'm slowing down, velocity and acceleration are opposite signs. My velocity was negative, therefore my acceleration is positive. So, I'm standing right here. Velocity now is,
Yeah.
like,
Zero.
a couple people worked it out. My position, displacement, acceleration, it is at the moment. Not because I'm stopped, but just because my velocity is not changing. So now I start to move. So when I go from rest to moving, what was my velocity? Okay, because I start moving in that direction.
So, like, which one would be, I guess, the more dominant one? Like, if your velocity is positive, if you're moving in the positive direction. Wait, hold on. I have to picture it. Because if you're walking in the positive direction, but you're slowing down,
Right?
would velocity would be positive, but acceleration would still be negative?
Yes.
Okay.
Or if I'm going in the negative direction and I slow down, my velocity is negative, my acceleration is positive.
Okay.
The biggest trouble I have students making here, the biggest trouble I see students have, is that they so associate positive acceleration with speeding up and negative acceleration with slowing down. And that is not necessarily the case. That is the toughest thing I've seen students try to bring. All right, so right now, again, my velocity is, enthusiasm would be okay. And then I start moving in the negative direction, so my velocity is still negative. You keep wanting to say positive. Do you want me to do one word that's positive?
I keep thinking acceleration. I think it's the way you're facing.
Hmm.
Yeah, that looks like negative to me.
Oh. And you actually could define the entire universe based upon you as the origin of everything. And the way you face, you have this rotating coordinate system every time you move. It is possible. It is not the simplest way, but it is possible. All right. So right now I'm at rest, velocity 0, then my velocity becomes negative. What was my acceleration as I went from rest to moving in the negative direction? Why? I heard.
You're speeding up.
Still trying to bring people with that. I'm at rest. Which way do I have to be? Which way am I going to be forced in order to move in that direction? So I saw one person point that way and one person point that way. If I'm standing here and someone wants me to move in that direction, which way will they push me? Is that positive or negative? So my acceleration is? It's negative. Force and acceleration are always hand in hand. If I'm pushed in the negative direction, my acceleration will be in the negative direction. So from here to this, that's negative acceleration. That's positive acceleration. as I stop. Swing it around. My velocity right now, right, as I start moving, what was my acceleration? Because I pushed in that direction. As I move in the positive direction and I stop, what's my acceleration? Somebody, I think, pieced it out syllable by syllable.
Negative.
Yeah. So so acceleration being positive or negative has a lot to do with which way you're already moving in, which way the force is acting on you. It is, again, not a speeding up, slowing down automatically. And we're gonna have to end it at that. So next time on Monday, after we do any questions, then we'll talk about sort of the introductory test level problem, and then we'll do a test level problem where you get to do this for something more complex. It will be epic. And Shay, I apologize, for some reason I'm getting your names backwards.
It's okay.
Hopefully I'll break myself of the habit.
Can I ask you a question about the, lab really quick?
Yes.
Okay. So I was graphing, yesterday, and I was trying my best to put everything on one graph, both balls on one graph,
Right.
but it was a hot mess.
Okay, you're doing it on the computer?
I am.
Okay.
And I tried to make it two different colors, and between that and the equations, it just looked like, to me, it looked like a hot mess. I don't know how you would look at it.
All right, if the issue is you're printing in black and white and having trouble differentiating, or you're not even that?
No, it just
okay.
looks a mess. I don't mind putting it on the same graph. I had a hard time figuring out how.
Did you watch the video? The video was confusing, or?
No, I could do the single graph,
Right,
but then kind of putting it, my husband had to help me, and then I lost it, and then I was like, I accidentally deleted it, and then I tried to figure it out, cause he was trying to work with my kids, and it was a mess. But I realized that when we first did it, I was like, this is a mess, and then I tried to change the color, and it still, to me, looked like a mess. I don't know how you would look at it,
all right.
but I've managed to get it on two separate graphs,
But not one.
but not one, and I don't mind trying to figure out again how to put
If-
it on two different graphs.
If
not
you
the
put
same
them on
graph.
separate graphs,
Mhm.
because the directions explicitly say on the same graph, there will be a penalty for that.
Okay.
So the question is, how much is that worth it to you?
Well, I mean, I wanna get it done the way it's supposed to be done.
Right, so, I don't suppose you have it on flash drive, do you?
I don't, unfortunately, no, I have it on my husband's computer.
All right, how do you wanna handle this? We could go over to the computer and I could do a quick example in front of you.
That would be perfect, because he even had a hard time trying to figure out how to get it on two graphs. It took him an hour to do that.
Okay, all right.
And between him and I was just like, forget it, I'll just ask him in the morning.
Okay. And,
I just wanted to hear her.
okay,
My
well,
partner.
let's enter to the computer and see what we can do.
Let me get my phone. My husband is like the genius when it comes to Excel, but he gets so busy with work that sometimes I'm just like, never mind, it's not even worth asking.
His world does not revolve around you?
No, it doesn't. No matter how hard I try.
Good luck with that.
Yeah, I know. It's been 14 years, you know, just.
Something that I don't think people tell you in advance, but when you hit the 20-year mark, you
Mhm.
no longer have to listen to your spouse.
He started that at like year 10.
Well, some
I
people
was
are
in my
advanced.
parents' own about
That's okay, I started at year 2, so.
All right, so why don't we just, drop heights, I'll just
Looking at my phone.
make up numbers here. Skip one. Alright,
Here.
downside one. And that's it, yes it does. So. And. Oh. That seems awfully big there. I want something at least remotely not horrible. All right. So insert chart scatter plot. All right, so automatically it's come up with two of them because I have sort of my X values there and then the two Y values side by side.
Gotcha.
And it assumes it's gonna do that. Now, it doesn't necessarily help you if you don't have it formatted that way. And then I would go to quick layout
You did it well, that's why.
and then add trim line. We'll do it another way. It automatically comes up as linear. You wanna click those two buttons down there. And that is for the orange one. Yeah, there's a lot of overlap here, so I'm trying to put this equation so it's
Right.
gonna be closer to the orange line. We'll find out when we have the blue line. And then add trim line, display those. All right, and so put that near the orange line and.
Can you get around that by making the, well, I don't have to mark these.
Well, in,
I can make it two different colors.
all right, so if you want to, if you're gonna print in black and white and you
Mhm.
need something else, so let's go to, I need to make sure I click on the dot and not the line itself. Nope, that doesn't do it.
Oh, I would print it in color anyway.
All right, so there are the dots right there. Now it's a matter of where do I find it? Marker options, and then I can change, so built in, then I can change that to a different symbol.
Okay, gotcha.
And then my line itself, I can, I can change the width of it, and, there we go, dash type. I can make that one solid, so I can differentiate that way if you're doing black and white.
Okay.
Okay.
That was the part we were having trouble figuring out, so.
Ah, okay.
So I was like, forget it, we'll just do it in two for right now, and then I can ask him later.
All right, and then don't forget, you'll need to change access titles and chart
Yeah.
title. All right, so if you have just one of them, so let's get rid of this data. Or. Really? X. What is it doing? All right. All right, so I have that set of data, I want to add something to it. So I click somewhere in here and do select data. I want to add the X values are going to be my drop height. And my Y values, might have to delete that first before I do it. I'm going to be right there. And so I don't have a name for it because I left that off. And now I have the second set of data, which I can then do add trim line. I think that's the new one. Okay. Oh wait, that's the steeper slope. So that would be for the blue line. This is for the orange line. Now your data will not be as overlapped as this, which is one of the reasons why I wanted two balls of very different downsides.
Sure.
And I lost the place to put my title, so I would come over to, so I need to click on that, and then my design and format comes up. And now I have a place to put my chart title.
Gotcha.
The trend lines disappeared because it's Excel.
It think the first part will get me,
Okay.
will get me through to where I need to be.
All right.
Thank you so much, I appreciate you
Certainly.
taking your time.
Yeah.
So, I'll get my book. Have a good rest of your day.
You too.
Thank you.
And Shay.
Yes.
I'm trying to get to the habit here. Or perhaps your parents named you wrong.
Maybe.